Idaho Territory, South Fork of the Salmon River. January 4th, 1887. A freezing rain band swept the canyon from midnight to dawn, plating every exposed surface with 0.6 of an inch of glaze ice, confirmed by United States Signal Service observers in Warren. Air temperature 8 degrees below 0 Fahrenheit at daybreak. Wind calm but cold, trapped by inversion. Snow depth at cabin fronts ranged 26 to 34 inches. Drift crust unstable under a man's step. Most canyon cabins built between 1884 and 1886 used flush sills, strap hinges, and 5-inch foundations, easy to raise in a week, but vulnerable when freeze-thaw cycles heaved the sill 3/4 of an inch and locked doors in place. Yet a winter supply ledger dated 1888 contains a spare line. Door worked free after icefall, lifted by hand. 2 cabins in the same drainage were found sealed shut. Both occupants spent hours chiseling free. One cabin opened with 2 fingers. The difference came down to measurements. One threshold wrote over the ice instead of into it. Signal Service Weather Log. Record of canyon inversion patterns and freeze-thaw cycles. Rime accumulated on exposed rafters throughout December 1886, forming thin needles of ice that grew outward from every structural edge. The phenomenon was common in Salmon River Canyon's mid-elevation benches, where cold air pooled at night and remained trapped by steep walls until mid-morning sun burned through. United States Signal Service logs recorded at Warren, 28 miles northeast, showed consistent patterns for canyon winters, low temperatures ranging from 5 below to 30 below 0 Fahrenheit, 80 to 110 freeze-thaw cycles per season in mid-canyon benches, and 4 to 8 feet of seasonal snow compressed into uneven drifts by downdrafts funneling through side drainages. Newcomers to the canyon assumed log walls and a tight door were sufficient. They built quickly, using methods that worked in milder climates or lower elevations. Experienced canyon residents understood different threats: ground heave from frost penetration, wet snow creep that pushed against foundations, and ice glazing that turned every horizontal surface into a single frozen mass. 3 groups occupied the South Fork drainage during the winter of 1886 to 1887. Trappers worked the Warren mining district, checking lines along tributary creeks. Homesteaders held benches on the South Fork, building cabins and clearing land before proving up their claims. Mail carriers traveled the supply trail from Grangeville, recording trail conditions and noting blocked access points in their route logs. A notice posted at Warren in 1885 stated plainly, "Glaze storms uncommon but severe. Doors freeze solid." The warning reflected accumulated experience from previous winters when freezing rain. Events created conditions that sealed cabin entries for hours or days. The pattern was consistent. Sills raised 6 inches above grade remained functional throughout winter. Sills built flush to ground level failed every second storm, requiring hours of chipping and prying to break the ice bond between door and threshold. The question was not whether ice would form. The question was where the door sat when it formed. Strap hinge with 3/8 inch pin. Standard Frontier hardware showing stress cracks from ice-forced movement. A hinge creaked at Warren Supply Trail Depot on December 12, 1886, its iron surface coated with grit, blown in during the previous day's wet snowfall. The sound was familiar to anyone who had wintered in the canyon. Metal fatigued by repeated stress, pinholes worn oval from forced movement, straps bent where ice had leveraged the door against its frame. Typical frontier doors of the 1880s used simple, fast construction methods. Planks ranged from 3/4 to 1 inch thick, assembled edge to edge to create a panel 32 to 34 inches wide. Strap hinges with 3/8 inch pins were surface mounted to the door and frame, creating a pivot point that allowed the door to swing open. Sills were positioned 4 to 6 inches above grade, a compromise between ease of construction and weather protection. This height kept the threshold above most rain splash and moderate snow accumulation, but it was not enough to prevent problems when ground frost heaved the foundation. Frost penetration in canyon soils reached depths of 18 to 24 inches during sustained cold periods. Disturbed soil beneath cabin foundations loosened during construction, absorbed moisture, and expanded when frozen, lifting sills by half an inch to 1 full inch. This heave was invisible until the door stopped functioning. Chinking between logs used a traditional moss and mud mixture packed into gaps and allowed to dry. The mixture was effective at blocking wind, but it also acted as a wick, drawing meltwater from daytime thaw events toward the door frame where it pooled and refroze at night. Nicholson's Carpenter's Manual, published in 1875 and available at supply depots throughout the West, warned that flush thresholds invite wet and ice. The manual recommended raised entries for any structure exposed to freezing conditions, but most builders ignored the advice in favor of speed. The trade-off was clear. Fast construction prioritized immediate shelter over winter survivability. A cabin could be framed, roofed, and occupied in 1 week using standard methods. That speed was essential when racing against the first heavy snowfall, but light planks combined with external hinges and low sills created 3 adhesion points where ice could lock the door solid, along the bottom edge where the door met the sill, at the hinge pins where glaze sealed metal to metal, and at the eye latch side where the door pressed against the frame. One design placed movement above the freeze line instead of against it. Freight Ledger from Grangeville Mercantile lists hardware pricing and pack weight limits. Mule breath froze along the lash rope on the South Fork Pack Trail December 20th, 1886. Each exhale left a white crust that built up throughout the day, adding weight to the line and stiffening the hemp until it required force to tie or untie. Freight logistics controlled what could be built in the canyon. Pack animals carried 80 to 120 pounds maximum, a limit set by the steep grade and narrow trail conditions. The distance from Grangeville supply points to South Fork benches measured 28 to 33 miles, depending on route. Lead times in December stretched to 6 to 9 days when snow depth exceeded 2 feet on the ridgeline crossings. Hardware was expensive and heavy. Ledgers from Grangeville Mercantile listed strap hinges at 15 to 20 cents each, double that price for reinforced models with heavier iron. Plan boards cost 25 cents per piece, a significant expense when most structural lumber was hand-hewn on-site from local timber. A single homesteader working alone could fell, limb, and skid 10 to 14 lodgepole pine logs per day under favorable conditions. Joinery work, notching corners, fitting sills, shaping planks, reduced that rate to 6 to 8 logs per day. Time mattered. Late-season builders faced a shrinking window between the last pack train and the first impassable snowfall. Water access required daily effort once streams froze. Homesteaders chopped through ice that thickened to 6 inches or more by January, creating access holes that refroze overnight and required renewed effort each morning. Fuel consumption ranged from 1 to 1.5 cords per month for a small cabin, depending on construction quality and outdoor temperatures. Most canyon cabins used only local materials, lodgepole or tamarack logs for walls, moss and clay for chinking, bark or split shakes for roofing. Iron hardware was minimized to reduce cost and freight weight. The ice storms of 1884 through 1886 created a pattern in mail carrier logs and settler journals. Entries repeated the same problem. Doors frozen solid, hours lost to chipping and prying, interior heat lost while the door stood open during ice removal. Every recorded failure shared one feature. No door had upward travel. Every threshold was fixed in place, and every door was trapped against it when ice formed. The solution required recognizing that movement, not strength, would break the bond. Ethnographic survey notes. Documentation of Shoshone. Winter shelter design emphasizing raised entries. Snow slid from a barked larch roof in a single sheet, the sound reaching across the drainage in the still air of a January afternoon. The phenomenon was common on steep-pitched roofs where snow accumulated but could not bond to the smooth bark surface. When warming or wind broke the adhesion, the entire mass released at once. Regional survey notes from the 1850s through 1880s documented building strategies adapted to deep snow conditions. These records were compiled by military surveyors, territorial officials, and ethnographers studying indigenous construction methods. Shoshone winter shelters in the Salmon River region emphasized raised entry points that allowed snow to accumulate without blocking access. Brush and bark structures were built with door openings positioned 1 to 2 feet above ground level, creating a natural step that remained functional even when snow depth exceeded 3 feet. The design was not decorative. It solved a fundamental problem. Snow creeps, and any entry at grade level will eventually be buried or blocked. Scandinavian settlers in Minnesota and Wisconsin brought knowledge of lift doors used in barn construction. These doors featured vertical adjustable lower edges that could be raised or lowered depending on snow depth. The mechanism was simple. The door hung on standard hinges, but the bottom edge rested on skids or wore shoes that could slide in grooved tracks. When snow accumulated, the door was lifted, and wooden pins held it at the higher position. Great Lakes trappers used skid shoes under winter doors, removable boards fitted to the door bottom that elevated the edge by 2 to 4 inches. The shoes prevented the door from freezing to the threshold and allowed it to ride over shallow drifts without binding. Settlement-era manuals referenced adjustable thresholds as an established technique for cold climate construction, though the practice remained uncommon in Rocky Mountain cabins. The reason was straightforward. Adjustable mechanisms required additional labor, more precise joinery, and often imported hardware. Canyon builders between 1884 and 1886 followed standard fast build practices. Time pressure, limited tools, and freight costs made elaborate entry systems seem wasteful. The idea of a door that moved relative to its threshold existed in multiple traditions. The missing element was not knowledge. It was the allocation of labor to implement the design where conditions demanded it. Bent nail reused 4 times. Physical evidence of hardware scarcity and material reuse. A bent nail was driven into a door jamb at a South Fork bench cabin in autumn 1886, its head mushroomed from repeated hammering. The nail had been pulled, straightened, and reused at least 4 times, each cycle flattening the head and weakening the shaft. Hardware scarcity made every piece of iron valuable. Tools available to canyon homesteaders included the froe for splitting shakes, the broad axe for rough shaping, the draw knife for fine work, the auger for drilling, and the whipsaw for cutting planks. These tools were sufficient for standard cabin construction, but they required skill and time to produce dimensionally consistent lumber. Sliding mechanisms presented a specific challenge. A door riding on runners demanded smooth, planar surfaces with minimal variation in thickness. Standard frontier lumber, logs hewn flat on 2 or 4 sides, varied by 1/4 inch or more across a single plank. That variation was acceptable for wall construction where chinking filled gaps, but it was problematic for any system requiring precision fit. Store ledgers from Grangeville listed planed boards at 25 cents each, a premium price reflecting the labor required to produce them. Most homesteaders avoided planed lumber entirely, using hewn logs for all structural elements. Tamarack presented an exception. The species grew abundantly on mid-slope canyon benches between 4,000 and 6,000 feet elevation. Tamarack wood was dense, straight-grained, and resistant to wear. More importantly, it planed smoothly with a draw knife, producing surfaces that were consistent and durable. A competent woodworker could plane a tamarack board to within 1/8 inch thickness tolerance using hand tools. The work required patience, repeated checking with a straight edge, and careful attention to grain direction, but it was possible without powered equipment. The mechanical advantage of tamarack runners became clear under load. Softer woods like pine or fir compressed under repeated sliding friction, creating grooves that increased resistance over time. Tamarack maintained its surface integrity through hundreds of open-close cycles, wearing slowly and evenly. Dimensional inconsistency made sliding sills unreliable in most applications. But using the right wood, locally available and properly worked, removed that constraint. The material existed within a half-day's haul. The method required recognizing its properties and allocating the labor to exploit them. Tin of tallow mixed with graphite, lubricant compound adapted from ore cart maintenance, tallow heated in a tin, skimmed once to remove impurities, then darkened with graphite powder. The mixture was standard in mining operations for lubricating ore cart wheels and tracks, but it served equally well for any application requiring low-friction surfaces in freezing conditions. The slide-sill door design began with the threshold. Standard cabin sills sat 4 to 6 inches above grade. The improved design placed the threshold 9 to 11 inches above ground level, creating a raised platform that remained above typical snow accumulation and kept the critical sliding surfaces away from ground moisture and frost heave. 2 runners formed the core of the mechanism. Each runner measured 2 1/4 to 2 1/2 inches thick, hewn from tamarack and planed to a smooth, level surface. The runners were mounted parallel to each other, spaced to match the door width, and secured to the threshold beam with wooden pins driven through pre-drilled holes. The runners had to be level within 1/8 inch tolerance across their entire length. Any deviation created binding points where the door would catch during operation. Achieving this tolerance required careful planing, repeated checking with a straight edge, and shimming where necessary to compensate for minor variations in the underlying threshold beam. The door bottom was fitted with a U-shaped shoe carved from dry fir. The shoe wrapped around the lower edge of the door, creating a channel that rode along the tops of the 2 runners. The fit was close but not tight, approximately 1/16 inch clearance on each side, allowing the door to slide freely while preventing lateral wobble. Vertical travel ranged from 1.5 to 2 1/4 inches. When the door was lifted, the shoe rose along the runners, reducing the contact surface between door and threshold. When lowered, the shoe settled back onto the runners, sealing the gap at the bottom of the door against wind and snow. The lubricant was critical. Tallow mixed with graphite was applied to the runner surfaces before installation and renewed monthly during winter. The graphite provided dry lubrication that remained effective at temperatures well below 0 Fahrenheit, while the tallow filled microscopic surface irregularities and prevented direct wood-to-wood contact. The mechanical principle was straightforward. When the door shoe lifted, the effective contact area between door and threshold reduced dramatically. Ice adhering to the exposed lower surfaces of the runners broke free under minimal force because the bond area was small and the door mass was moving upward, away from the frozen surfaces, rather than scraping across them. A door that rides upward cannot be frozen downward. Draw knife with worn handles, tool used for planing tamarack runners to precise tolerance. Thin chips curled from a draw knife stroke on tamarack, falling in tight spirals that indicated proper blade angle and sharp edge. The work was slow but essential. Each runner required 3 to 4 hours of planing to achieve the smooth, level surface necessary for reliable operation. Construction began in mid-October 1886, allowing 6 weeks before heavy snowfall typically closed the high passes and made freight hauling difficult. The build sequence followed a specific order, each step dependent on the accuracy of the previous work. Stone footings were set first, sunk below anticipated frost depth, 24 to 30 inches in canyon bench soils. The stones provided a stable base that would not heave during freeze-thaw cycles, eliminating the foundation movement that compromised standard cabin doors. The threshold was assembled next, using 2 parallel beams hewn from lodgepole pine and pinned to the sill logs with wooden dowels. The threshold sat 9 inches above the cabin floor level, creating the raised entry that would keep the Iowa runners above snow and ice accumulation. Runners were aligned on the threshold and checked repeatedly for level. A carpenter's level, a simple wooden frame with a suspended plumb bob, confirmed horizontal alignment. The runners were secured with pins driven at 12-inch intervals, each pin seated firmly and the exposed ends trimmed flush. The door itself was planked from tamarack boards, each board 1 inch thick and fitted edge to edge. Horizontal battens reinforced the interior face, preventing warping and distributing stress across the panel. Total door weight ranged from 28 to 36 pounds, heavy enough to seal against wind pressure, but light enough for one person to lift and operate. The door shoe was carved from a single piece of dry fir, shaped to wrap the bottom edge of the door and create a smooth channel that would ride along the runner tops. The shoe was secured with wooden pins driven through the door planks from the interior side, ensuring no metal fasteners were exposed to weather. An over-door drip lip was installed above the frame, angled at 10 degrees to direct rain and snowmelt away from the door face and threshold. This detail was standard in better frontier construction, but often omitted in fast builds. Total construction time, 5 days. A standard door required 2 days using conventional methods. The 4 additional days of labor removed an entire category of winter hazard, the sealed entry that trapped occupants inside or left them stranded outside with no access to shelter, fuel, or supplies. Ice film preserved between runner and shoe, physical evidence of frost formation patterns. Ice film cracked along the runner surface under minimal upward force, the fracture audible as a soft tick in the still morning air. The test came in early December 1886, after the first significant freeze following a period of wet weather. Field performance data came from direct observation and comparison with neighboring cabins. Standard doors in the drainage began experiencing freeze-up problems when ice thickness reached 3 to 8 millimeters, approximately 1/8 to 1/4 inch. At that thickness, the bond between door edge and sill required 40 to 90 pounds of force to break, often resulting in damaged hinges, split planks, or splintered sills. The slide-sill door cleared with under 5 pounds of upward force. The calculation was straightforward. A 28 to 36-pound door resting on tallowed fir runners created a friction coefficient low enough that lifting the door by its handle broke the ice bond immediately. The ice did not have to be chipped or melted. It simply released when the contact surfaces separated. Multiple freeze-thaw cycles tested the system through December. Each cycle deposited a thin layer of ice on the runner surfaces, moisture from melting snow or condensation that froze overnight. Each morning, the door lifted free without resistance beyond the RE, normal mechanical friction of the sliding mechanism. The raised threshold prevented a second failure mode, soil heave. Standard cabins with low sills experienced gradual jamming as frost penetrated beneath the foundation and lifted the entire threshold structure. This heave was cumulative, worsening throughout winter as the ground froze deeper. Doors that functioned in November became progressively harder to operate by January. The slide-sill threshold, mounted on stone footings set below frost depth, remained stable. No heave occurred, no progressive binding developed. The door operated with the same mechanical ease in midwinter as it had during initial installation. The tallow graphite lubricant maintained a barrier approximately 2 millimeters thick between the shoe and runners. This layer prevented molecular adhesion, the direct contact between surfaces that creates strong ice bonds. Even at 15 below 0 Fahrenheit, the grease remained pliable enough to allow movement. A 2 millimeter grease layer outperformed 30 pounds of chopping force. The comparison was not theoretical. Neighboring cabins required repeated chipping sessions throughout winter, each session consuming 1 to 2 hours of labor and exposing the interior to heat loss while the door stood open. The slide-sill door required no chipping. It lifted, it opened, it closed. The mechanism functioned exactly as designed through conditions that immobilized every conventional door in the drainage. Signal Service Ice Measurement. Documentation of the January 4th glaze event. Ice bridged from sill to snowpack in a single continuous sheet, forming overnight as freezing rain fell through air cold enough to freeze on contact. The event occurred across the South Fork drainage between midnight and dawn on January 4th and 5th, 1887. United States Signal Service observers at Warren recorded the storm metrics: 0.6 of an inch glaze accumulation measured using a flat collection plate. Air temperature at dawn, 8 degrees below 0 Fahrenheit. Wind, calm, but cold air remained trapped in the canyon by thermal inversion, preventing mixing with warmer air from above. Snow depth at cabin sites ranged from 26 to 34 inches before the storm. Drift creep during the glaze event added 2 to 3 inches as wind-transported snow bonded to the ice surface, creating a consolidated mass that connected ground level to any structure touching the snowpack. Neighboring cabins were sealed by morning. Mail carrier logs from the following week noted multiple instances of doors frozen tight, requiring extended effort to gain entry. The pattern was consistent. Every cabin using standard construction with flush or low sills experienced complete immobilization of the door. The adhesion occurred at 3 points simultaneously. Ice formed between the door's bottom edge and the sill, creating the primary bond. Ice sealed the hinge pins to their mounting brackets, preventing rotation. Ice filled the gap between door edge and frame on the latch side, welding the surfaces together. Breaking any one of these bonds required significant force. Breaking all three simultaneously, necessary to open the door, required force sufficient to damage the structure. Hinges tore from frames, sills split lengthwise, door planks cracked. The alternative was hours of careful chipping, working from outside if possible, or from inside if the occupant was trapped. The slide-sill door faced the same ice accumulation. Glaze coated the exposed surfaces of the threshold and runners. Ice bonded the door shoe to the runner tops, where they remained in contact overnight. But the runners sat inside the sheltered door frame, protected from direct precipitation and shielded from the worst of the glaze accumulation. The exposed surfaces, the outer edges of the runners and the lower face of the door, received ice, but the critical sliding surfaces remained relatively protected. More importantly, the vertical lift mechanism meant the door did not have to break the ice bond by scraping across it. The door lifted, the bond broke, and the door slid free. The storm provided the test no builder wanted, but every design eventually faced. Wooden door handle with wear marks. Physical evidence of lifting grip pattern. The soft scrape of wood lifting against greased runners, then silence. The door opened on the morning of January 5, 1887, using 2 fingers on the handle and an upward pull that required less force than lifting a water bucket. Quantified differences between standard and slide-sill performance became clear under identical conditions. Standard door breakaway force after the glaze event measured 40 to 90 pounds, depending on ice thickness and bond area. The force required to overcome hinge friction, break the sill bond, and separate the latch side seal exceeded what one person could apply safely without risking injury or structural damage. The slide-sill door required less than 5 pounds of force. The calculation derived from basic mechanics. A 32-pound door with a friction coefficient of approximately 0.15 on tallowed runners required 4.8 pounds of upward force to overcome static friction and initiate movement. Ice adhesion added negligible resistance because the bond area was small, limited to the narrow contact line between shoe and runner, and the lifting motion separated the surfaces immediately. No hinge distortion occurred. The hinges on the slide-sill door served only to support the door's swing once it was lifted clear of the runners. They experienced no stress from ice breakage because no ice bond had to be broken at the hinge points. No sill fracture occurred. The stone-footed threshold remained stable and undamaged because no lateral or downward force was applied during operation. The door lifted vertically, then swung horizontally. Both motions aligned with the intended mechanical function of the system. Contrast between expectation and result was stark. Standard construction assumed strength would overcome the problem: heavy doors, strong hinges, robust sills. The assumption failed when ice adhesion exceeded structural limits. Doors that seemed solid proved fragile when force concentrated at failure points. The slide-sill design assumed movement would eliminate the problem. Ice could form, but it could not prevent operation because the door was not fighting the ice. It was riding over it. Force that would normally splinter a door jamb or tear hinges from their mounts now cleared the entry in seconds. The door lifted, the shoe separated from the runners, ice fractured along a narrow line, and the door swung open. Movement, not strength, won the test. The principle was not abstract. It was measurable, repeatable, and absolute under the conditions present in Salmon River Canyon during winter 1886 to 1887. Fuel consumption log. Comparative data showing wood savings from maintained access. The woodpile remained accessible immediately after the January 5th glaze event, its surface crusted with ice but reachable without delay. Immediate fuel access prevented the cascade of problems that followed door failure in neighboring cabins. Survival logistics depended on maintained access to three critical resources: firewood for interior heat, the chimney for smoke clearing, and the surrounding area for livestock checks or emergency egress. Standard cabins sealed by ice lost all three simultaneously. Fuel access was primary. Interior temperature in a small log cabin dropped approximately 1 degree Fahrenheit per hour when the fire went out, assuming outdoor temperatures of 0 to 10 below. A cabin at 65 degrees Fahrenheit at midnight would reach 40 degrees by dawn if the fire was not maintained. Restarting a fire from cold coals required kindling and careful tending, resources stored inside, but useless if the door could not be opened to bring in more wood. Cabins sealed by the glaze event faced a choice: burn interior furnishings to maintain heat while chipping through the ice, or let the fire die and accept the cold while working to clear the door. Either option consumed hours and resources. Fire pans, metal containers filled with hot coals and placed against the frozen sill, were the standard method for melting ice bonds. The process consumed 1 to 2 pounds of fuel per attempt, required constant attention to prevent the pan from freezing to the surface it was meant to thaw, and took 30 minutes to 2 hours depending on ice thickness and outdoor temperature. Chimney clearing was secondary but essential. Snow and ice accumulation on the chimney cap could block draft, forcing smoke into the interior. Clearing required exterior access, impossible if the door was sealed. Livestock checks mattered in homesteads with animals. Cattle, or horses sheltered in nearby structures, required daily attention. A sealed door delayed those checks by hours, risking animal welfare and potential loss of valuable stock. The slide-sill door eliminated these cascading failures. The door opened immediately. Fuel access was uninterrupted. Interior heat was maintained. Chimney clearing proceeded on schedule. Livestock checks occurred without delay. One neighboring cabin recorded in a January ledger: 3 hours chipping door free, fire nearly out. Used quarter cord extra wood this week for melting and restoring heat. The slide-sill cabin recorded: door lifted as usual. A 2-finger lift replaced a full day's lost heat, hours of dangerous labor, and measurable fuel waste. Every storm cycle. Runner plank with decade of wear. Physical evidence of long-term durability. Runners polished by a decade of use showed wear only on their upper edges. The wood darkened and compressed where the door shoe had traveled thousands of cycles. The wear pattern was even, indicating consistent alignment and proper load distribution throughout the mechanism's service life. Survey notes from 1890 through 1904 documented the gradual appearance of raised sill and adjustable door designs in backcountry structures across Idaho and Montana territories. Forest Service ranger stations, trapper line cabins, and remote pack stations began incorporating variations of the slide-sill principle. Thresholds raised above snow level, doors riding on greased runners or fitted with lift mechanisms, and lubricant maintenance noted in station logs. A ledger entry from a Montana trapper cabin dated 1902 stated, Slide track re-greased, tallow mix renewed, door working free. The note indicated routine maintenance of a system that had become standard practice in areas experiencing heavy snow and glaze conditions. The diffusion pattern followed practical need rather than formal instruction. Trappers and homesteaders who experienced door failure during severe winters sought solutions. Those who observed functioning slide-sill designs during visits to neighboring cabins adopted the technique. Knowledge spread through direct observation and word-of-mouth recommendation, not through manuals or institutional guidance. Variations adapted to local materials and specific conditions. Some builders used skid shoes instead of full runners, creating a simpler system with less precision requirement. Others incorporated lift pins that allowed the door to be locked at a raised position during deep snow periods. A few used metal tracks salvaged from mining operations, creating permanent installations that required minimal maintenance. The common element across all variations was the principle: raise the threshold above the freeze line, reduce friction through lubrication, and allow vertical movement that breaks ice bonds rather than forcing the door through them. Regional timber surveys from the early 1900s show increased use of tamarack in door and threshold construction, reflecting recognition of the wood's superior wear resistance and workability. Freight ledgers show steady demand for tallow and graphite in winter supply shipments, indicating adoption of lubrication maintenance as standard practice. The method spread where conditions demanded it. High-elevation cabins in heavy snow regions adopted the design almost universally by 1910. Lower-elevation structures in milder climates continued using standard construction, which remained adequate for their conditions. Methods travel where conditions repeat. The slide-sill door answered a specific problem in a specific environment, and it persisted wherever that problem remained relevant. Tamarack runner fragment with graphite staining. Preserved example of the lubrication system. A surviving tamarack runner, darkened with old graphite and worn smooth by decades of use, represents the mechanical principle that redefined winter entry in canyon country. The fragment was recovered from a dismantled line cabin in the Salmon River backcountry, its surface showing the characteristic polish of long service and proper maintenance. The slide-sill door reframed winter access as a mechanical problem rather than a strength problem. Standard construction assumed force would overcome ice. Thicker doors, stronger hinges, more robust sills. The assumption failed when ice adhesion exceeded structural capacity or when breaking the bond required force that damaged the very elements meant to provide access. The improved design eliminated the confrontation. Ice formed, but the door rode over it. Friction remained low. Movement remained possible. Access remained guaranteed. The innovation was not invention. Raised thresholds existed in multiple building traditions. Sliding mechanisms were known. Lubrication was standard practice in industrial applications. The contribution was synthesis, combining known elements in a configuration suited to the specific demands of high-elevation, freeze-thaw environments where door access was life-critical. Early Forest Service cache construction in Idaho and Montana territories shows evidence of the design. Standardized plans from 1908 through 1920 include specifications for raised thresholds with runner systems, indicating institutional adoption of the technique. Some of these caches remained in service through the 1960s, testament to the durability of properly executed slide-sill construction. The broader lesson extended beyond doors. Canyon survival required understanding that force was not always the solution. Sometimes the solution was reducing resistance, changing the point of contact, or allowing movement instead of creating rigidity. The same principle applied to tools, structures, and methods across frontier disciplines. A door sealed by ice represented more than inconvenience. It was a barrier to fuel, to escape, to assistance. It was a failure point that turned shelter into a trap. The slide-sill door eliminated that failure point through 2 inches of vertical travel and a thin layer of grease, minimal intervention that created absolute functional advantage. The door that opened with 2 fingers after freezing rain saved no lives in dramatic fashion. It saved them quietly, repeatedly, by ensuring that the fundamental necessity, an open exit, remained available regardless of conditions outside. In a region where freezing rain could turn a door into a wall, a greased 2-inch runner safeguarded the frontier's most basic requirement, the ability to leave.